Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. Now, first of all, Rose in Kings Lynn says, why does music always lift your mood? Dave?
It's a very, very interesting question. It's not my area of expertise, so I'm only really speculating. There's definitely quite a lot of evidence that we're very hardwired to find music interesting and for it to affect us. If you look at ancient societies, sort of tribes in Africa or anywhere, think what they use music for, it's quite often in kind of sort of tribal bonding ceremonies, sort of if they're going to, in any sort of important ceremony to make it feel more important, so everyone kind of concentrates on it. Or if you're going to war to get very angry, so you're angry enough to go off and fight somebody else. And so it's kind of almost a sort of social way of making everybody, it's used as a social way of making everyone's mood the same, which can be useful socially for the group. How it works on a kind of brain level, I have absolutely no idea, I'm afraid. But it's certainly a very, very interesting question.
Thanks for that, Rose. I hope that's helped you. And I think everybody's different as well, because, you like dancing, but you're not really a big music fan, are you?
Yeah, music will affect my mood. But yeah, I've never... And the other thing is that it's also quite often to do with what you remember, where you have first heard the music. If you first hear music and you're doing something great, then it wires straight into your memory and you get kind of memories of the great night out you first heard it. Whereas other times, if it's somehow associated with something awful, then you'll bring back those memories. So quite a lot of it is to do with what you associate the music with, and that affects your mood.
Mike in Colchester says he has a watch with luminous dials on to help him see the time in the dark. He's just heard about a new invention, self-powered micro gas lights, which allegedly glow 10 times more luminous than paint. How does it work?
There's various different ways of making watches glow. The first one they used was radium paint. Now, radium is a radioactive product of uranium breaking down. It's radioactive. When the atoms break down, they fire out some radiation. You then mix it with something called a phosphor. When this radiation hits the phosphor, it gives the phosphor a load of energy, and then the phosphor absorbs that energy from the radiation and it re-emits it as light. So that's great. You produce a nice, beautiful, bright, glowing watch, numerals, whatever, and it's a nice paint. It's very easy to use. The problem is it's radioactive, and in fact, the first time they really discovered that radiation was dangerous was the women who were painting on the watch dials. They had this radioactive paint. They were licking the paintbrushes to get them nice and thin so as they could write on it, and they all got mouth cancer and throat cancer because of all the radium they were swallowing and sitting around in their mouth. And it was giving them cancer. So that has a problem. The more modern glow-in-the-dark things tend to be phosphorescent paints. These absorb energy from light, just from the daylight or from a light inside a room, and then give it out slowly over hours or minutes or hours. And so they'll glow reasonably bright. They'll be very bright to start with, and then they'll die off over a few hours, and after 2 or 3 hours they'll be almost completely dim. You won't be able to see them at all. I think the micro gas lights he's talking about use a different kind of radioactive substance called tritium. This is a form of hydrogen which is quite radioactive. It's got 2 extra neutrons with each proton, so it's quite an unstable atom. It can decay radioactively. And they put some phosphor in they have little tubes of this gas, then it can decay and hit some phosphor and make it glow. The reason why it's a lot safer is that if it breaks, it's a gas, and hydrogen is lighter than air, so it just floats upwards and away, and it won't stay on you very much. So it's far safer, and I think that's what he means by the micro gas lights.
Another Mike says, when was gunpowder first invented or discovered in England? And if Guy Fawkes had been successful, how much damage would he actually have done trying to blow up the Houses of Parliament?
Gunpowder was first discovered by the Chinese, or first invented by the Chinese in sort of probably somewhere around the 800s or 900s. They first started off using it for rockets and firecrackers and things, and eventually they started using it in guns, probably in sort of the 1100s in China. It then worked its way into the Islamic world in the 1200s, and I think fairly soon after that, it ended up coming to Europe. The first person who was thought to have written it down anyway was a guy called Roger Bacon, who was actually an English philosopher, and that was in the 1300s, or late 1200s. And then it sort of spread around Europe. So it had been around for a good 350 years before Guy Fawkes tried to blow up the House of Parliament. Exactly how much damage it would have done, I don't know, but I think it was 36 barrels, and that's quite a lot in quite a small room to start with. Because gunpowder, if you just leave it lying around outside and set light to it, it doesn't explode, it just burns very quickly. Because it's got the oxygen in with the fuel, so it's a mixture of carbon and saltpetre. Saltpeter's got a load of oxygen in it. The carbon from the charcoal will burn with the saltpetre, and the sulphur as well will burn with the saltpetre. So it's got all the fuel it needs, so it'll burn very quickly, but it doesn't explode. The way to make it explode is to put it in something contained, like a barrel. So it sets fire to it, it makes lots and lots of gas, and then that breaks the barrel. And he was putting it in a cellar under the Houses of Parliament. And so if you get lots and lots of gas suddenly in a cellar, nowhere for that gas to escape. So it probably would certainly have blown up everything above, which was, I think, where the king was supposed to be sitting. So I think it would have done a lot of damage if it had gone off.
A spacey question now. Dr. Dave, do satellites collect space dust after spending years in orbit, or if on a sheet of glass floating in space collects space particles? And that's somebody else called Mike. Thank you, all the Mikes tonight, sending us questions.
The Mikes are feeling particularly curious this week. Well, in some senses they do, but you wouldn't find it lying around on the satellite. The thing is about space, because there's no atmosphere there, even tiny particles of dust can be moving incredibly fast at many kilometres a second. So tens of thousands of miles an hour. So 20, 30,000 miles an hour. And when a particle hits anything at that speed, it's not going to sort of gently stop. It's going to hit it, and there's so much energy there, it's going to vaporise. And if you look at things which have been in space for a long time, they're covered with lots of little tiny pits where these little tiny lumps of space dust have crashed into it and just blown little holes in the surface.
Wow.
It's part of the reason why satellites can't stay up for very long, because all of their solar cells get all these little pits and damage. And they slowly get less and less efficient as less and less of them left. You can catch particles from space, but you've got to slow them down gently. There was a Stardust mission recently which had a thing called aerogel, which is the lightest solid substance we know of. It's sort of this very, very thin gel. Essentially you make a jelly out of a glass, essentially, and you take away all the liquid which you've made it from, and so you end up with this thing which is 99% air. And then when the particles hit that, they sort of slowly slow down rather than stopping immediately, and you can catch some of the particles. I think they sent one up and just left it in space, and they sent another one to the tail of the comet to catch the particles coming out the tail of the comet. So they do accumulate, but not quite in the way you were thinking.
Right, you can't go around with your feather dusting then and sort of flick them off in any way. Hello to John, who sent an email to say they don't use deuterium anymore. They use superphosphorus. Old watches from the 50s use radium, and then they switched to tritium. Is it tritium? Or, you can tell if it's tritium. It usually has two little T's either side of the name Swiss at the bottom of the watch dial, from John. So that's the thing. Thank you very much, John. Listening in the middle of nowhere, somewhere in upstate New York. He did send me a map, actually, to say where he was, but I never grasped it. It's so vast. Let's go to Alan, who's between Luton and Dunstable, and he says that he lives in Luton and can never seem to get a clear radio signal. He works a lot in Germany and South Africa, and when he's there, he wants to listen to a station he can lock on to one frequency and get a good quality signal. In England, however, stations seem to be dotted around 2 or 3 more places, so why can't we get a clear radio signal like he can get abroad? Dave?
It's a very interesting question. There's various different reasons why you might not be getting a good signal. One of them is that there's just not enough power getting to you from the transmitter. Depending on the landscape, it can be very differently easy to get a good signal. If you're living somewhere where there's a big mountain in the middle of a big flat area, then it's really easy. You put a transmitter on the top of the big mountain, then the transmitter can see everybody. Radio waves are kind of light. They like going a straight line. So anyone who can see the mountain will be able to get a wonderful radio signal, and it's all fine. In this part of the country, it's quite flat, so it's very hard to get a transmitter up very high, so it's quite hard to get a good signal. And also, if you're somewhere which with lots of small rolling hills, you can get lots of shadows from the hills, so it's quite hard to get a good signal. You also get problems with interference from other radio stations. If you're trying to squeeze lots and lots of radio stations in a small area, then you can get interference between them. So if the next one that's transmitting on the same frequency isn't quite far enough away and we're a very crowded island, then the two signals can interfere and you get a bit of both of them. And with FM, that's going to just kind of generally cause interference. With AM, you can sometimes hear both radio stations at the same time, which can be quite entertaining. Although not quite what you were hoping for.
No. We've got full attention to this programme.
So lots of reasons. Definitely with South Africa, there's not going to be very much interference because it's a very, very empty country. And depending exactly on the landscape, you might have a better designed area for transmitting radio waves to you.
Right, let's get your maths out now then, Dave. Trucker Martin says, if he was moving at 1 metre per second under the speed of light and fired a bullet, would it exceed the speed of light?
That's a very interesting question, and the simple answer is no. Nobody would see that bullet going faster than the speed of light. What Einstein worked out was that everybody sees light going at the same speed and they see nothing going faster than that speed. And everything else changes to make that work. It seems bizarre, but that seems to be the way the universe works. Time changes and space seems to change in order to make the speed of light appear constant everywhere. So if you fired the bullet, you would see the bullet coming out of the gun at 300 metres per second, but you'd also see light going at 300,000 kilometres every second in all directions, and everything would look normal. If I was standing still and you were going at 99.999 times the speed of light and saw you firing a gun, I would see the bullet coming out of the gun ever so slightly faster than you were moving, but still not as fast as the speed of light. But I would see you moving incredibly slowly, so it would look like you were moving 100 or 1,000 times slower than normal. So that bullet wouldn't quite go faster than the speed of light because your time has slowed down so much that it isn't going faster than the speed of light. So basically everything changes, so the speed of light looks constant and nothing can go any faster than it. So no, it wouldn't be going. No one would see it going faster than the speed of light.
Dr. Dave from The Naked Scientist is here in the studio answering your science questions. One here from Mark, who says, applicable to tonight, what gives fireworks their colour? Dave?
Okay, what they do, I don't know if you ever remembered at school doing an experiment where you got a Bunsen burner. And then
a Bunsen burner,
yeah. And then put different bits of wire in, and you got colours coming out of off the wires.
I can vaguely remember that, yes.
Okay, what you were doing is you're putting different metal salts on the wire. So if you put copper salts on the wire, you got a green flame.
Yes.
Sometimes you get a blue if you've got some other copper salts. Strontium makes a lovely red flame. Calcium makes a slightly less good red flame. Sodium makes a beautiful orange flame. It's such a beautiful, so good at emitting light, they use it for street lights. So street lights have actually got sodium metal in them, which they heat up and turn into a gas. They put a spark through and they glow. Neon is another gas which, if you put electricity through it, it glows bright red, which is why red neon tubes are red. Okay, so in a firework you want to produce colours, so basically all you have to do is get metal salts very, very hot, and different colours are different salts. The reason why the salts produce such beautiful colours is that when you got to turn them to gas first, when they're a gas, the electrons in them, they're a little atom with electrons flying around them, but the electrons are only allowed to be at certain energy levels. So they can only have certain energies. You can give them some energy so they can jump up an energy level and they can jump back down. When they jump back down, they give out this energy as light. And different amounts of energy produce different coloured lights, different coloured photons of light. So different jumps in energy produce different colours. So different metals have different jumps, they produce different colours. So basically put metal salts in and set fire to them and you get pretty colours.
Thank you for that. Zach in Assington says, why does music seem to sound better on the radio? That's an interesting one, Zach, because I just love listening to mine on my, in my car, CDs and things like that. But interesting. Dave?
It's interesting. Well, obviously it could be something to do with the beautiful way it's been introduced by the DJ. Or interesting noises coming from over there. But something they tend to do with radio, particularly FM radio, is they do what's called compressing it. that makes all the volumes the same. So if you've got a piece of music, particularly classical music, can go very quiet and get very loud and go very quiet. You put it through a piece of electronic. The problem with that, if you're driving along in the car with lots of background noise, you just can't hear the quiet bit. And if you turned it up loud enough to hear the loud bit, you'd be completely deafened. So they do something called compressing it, which makes all the volumes approximately the same. So it's a bit like having someone sitting next to a volume knob, and whenever it goes quiet, it turns the volume up. Whenever it goes loud, it turns it down again. So all the volume is about constant, roughly. Different radio stations do this different amounts, I think. Radio 3 hardly does it at all, and Radio 1 does it a lot. But that will affect how it sounds, and it will sound different. Other than that, maybe just like kind of slightly odd sound quality.
Stephen Corby. Hi, Dave. And so I'd like to ask, why is a tomato skin so tough that every time you cut it, you need an exceptionally strong knife? And how strong is it? With my gardening hat on, you see, I'd say you haven't watered them enough when you were growing them. But tomato skins can be really, really tough. Dave?
I guess the why is to stop creatures crawling in and eating a lovely tomato. Because if you're a tomato plant, you want big animals to eat it, not small animals. Because if a big animal eats it, then it eats a nice tomato. And if you've ever noticed, tomato seeds are covered with sort of jelly stuff.
Yeah.
That's to protect them in your gut.
Right.
So you can't digest them, and they come out the other end. And when they come out the other end, they've got a lovely lump of fertiliser with it. So the tomato plant's got a wonderful start in life because it's been moved away from its parent plant and it's surrounded by fertiliser. So it's wonderful, the tomato plant. But if small creatures like ants come and eat the tomato, then they're not going to carry the seeds away to a lovely place for them to grow. So it's probably to stop sort of small insects and things which can't transport the seeds around. I can't say I've done any experiment to say exactly how strong it is. It's quite strong, but once it does break, it tears very easily. Which is the reason why tomatoes explode so satisfyingly when you throw them at things. So,
really? Well, yeah, sometimes they just, inadvertently.
Because it's very strong but not very tough.
Yeah.
So it sort of splits very easily, which is what you want if you want big creatures. Because otherwise, if it was really tough, the big creatures would get bored of eating it because they'd have to fight so hard to get in.
Well, Steve's obviously fighting with his tomatoes. Maybe you need some stronger cutlery, Steve. Thank you very much indeed for that one. Adrian in Peterborough says, we make our own fireworks using custard powder. Is that possible, Dr. Dave?
Well, it's not quite the same as conventional fireworks, but you can certainly don't do this at home, or if you do, I didn't tell you to.
Please don't do this at home.
Basically, for something to burn very quickly, it needs a very, very large surface area because you need oxygen to get at the fuel. If you've got a big lump of wood or something, then the oxygen can only get at the surface of the wood. So only a small amount of the wood can burn at any one time, maybe only 1%. So it's got to burn 1% and 1% and then 1%. And so it burns very slowly over a period of hours. If you get paper, which is essentially a piece of wood which has been flattened out incredibly thin, it can burn sort of 50% of it can burn at once, and so it can burn very, very quickly because it's got much more surface area for its volume. If you get something like custard powder, which is tiny, tiny particles of a powder, and you spread that out and mix it with air, it's got a huge surface area, so it can essentially burn everywhere at once. It burns very, very quickly. And if you can blow it through a flame and ignite it, it will burn in sort of less than a second. And you can form big, nice fireballs out of it, although be aware that they can be very nice fireballs and they will move upwards. So it's very easy to burn yourself. And don't throw it downwards onto a fire unless you're being very careful, because the fireball will come up and catch your hand if you're not very careful.
Adrian, please don't make any more fireworks like that,
Be
please.
very careful. Or do it on a long stick or something.
Ooh. If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. We've got Tony on the A11, Dave. He says when he digs up a patch of garden, why does he find so many stones of all shapes and sizes? And how did they get there? And how long have they been there? I wonder where you live, Tony.
Yeah, I mean, certainly how long it takes, how long they've been there will depend on where you live. The stones in your garden fundamentally come out of rock somewhere. If you live somewhere simple, where you're on the side of a mountain or something, then you'll get the cliffs above you, you get freeze-thaw, so you get water getting in little cracks in the rock. It will freeze, it will expand, it will break rocks off the hillside, they'll fall down the hillside. Or you'll get roots from in the plants sort of working their way in amongst the rock and breaking it up and getting the nutrients out of it. And that can make stones as well. And so you get big stones, and then if they get moved around by water, they can get battered around and get made smaller, or they can get broken down by plants or just by weathering, and they slowly get smaller and smaller and smaller. And so the rock in your garden could have been put there, could have fallen off a cliff last week, or it could have been there for thousands of years. This part of the country, most of the stuff you're standing on was dumped here by ice sheets, particularly the sort of Norfolk and the East Coast, was dumped here by ice sheets in the last few ice ages. I think the one which got the ice sheets which got further south was sort of about 250,000 years ago. Yeah. And those sort of just ground rock up off the bottom of the North Sea, and it could have come all the way from Norway, or somewhere further north in the UK, down from Scotland, and they picked up rocks, and so they got mixed in with the ice, and the ice will slowly flowed south, and then eventually it melted, and the rocks are left, and they get dropped down, and they make up your garden eventually. Some areas you might get the chalk exposed, in which case you'll get chalk which breaks down quite quickly, but you get lumps of flint inside the chalk, and lumps of flint which make the lovely sort of smooth pebbles that have slowly developed from the chalk in the last, I think most of the chalks around here is Cretaceous, so sort of last 70 or 80 million years. But probably the ones in your garden have been sitting there roughly in the same place, apart from people lugging them around for at least 250,000 years, I'd have thought.
All right, interesting stuff. We've got John, who sent a text in. He says, "Hi, Dr. Dave. Is there a speed of dark?" Ooh, never thought about that one before.
That is a very good question. It sort of depends what you mean by the speed of dark. It's one of those questions where the difficult bit is defining what the question is. If you mean the speed at which a room will go dark, so if you have a room which is full of light and then you turn off all the lights, how long will it take to go dark? Then that's going to be something like the speed at the time it takes for light to get out the way is the speed of light. And so if you had a big empty room, it's going to be dark beforehand. So I mean, I think the only real answer to that question is the speed of light. The speed of dark is the same as the speed of light, because it's how long it takes light to get out the way. If that makes any sense.
Well, I guess it does one way or another, yes. Let's have one now that's coming by email from Thies, who says, why does footage shot in space not show any stars? I've always wondered that, actually. It's true, isn't it? You just get this sort of black, so how does that work?
And it's one of the things which all the people who think that the moon landings were a hoax always talk about. It's essentially the same reason why if you take a photo of if you imagine standing outside a tunnel and you take a photo of somebody just in the entrance to the tunnel, in the shadow of the tunnel, and you try and take a photo of them, and you've got lots of bright stuff around the tunnel because it's a nice sunny day, you'll see the tunnel all the trees and stuff around the tunnel incredibly well, but the tunnel's going to look completely pitch black. If you walked into the tunnel and took a photo of them in the tunnel, even if you didn't use a flash, they'd be bright enough for you to see. But if your camera is trying to take a photo of all the bright things as well, it's got to close down its aperture a lot to limit the amount of light that gets to it, because otherwise all the stuff outside the tunnel will be completely overexposed. So the tunnel itself is underexposed. If you go out into space, you're normally taking a photo of either the moon or a spaceman, an astronaut wandering around, or a space station or something. And those are illuminated by full sunlight, actually sunlight which is brighter than you ever get on Earth because it's not filtered through the atmosphere. And you're trying to take a photo of an incredibly bright thing, and there are stars behind it, but the stars compared to this incredibly bright thing are very dim, so you can't see them. If you took your camera and pointed them at space with no bright things in the way and opened up the aperture and took a nice long exposure, you'd be able to see the stars fine.
Wow. One here that we've got here from Tracy that's coming by email. How does my microwave affect my radio? Which is one of those strange things, actually, because they don't like things, do they? And also, if you've got your phone by your microwave, they don't seem to like each other. Well, mine don't anyway. How does that work, Dave?
probably the reason why the microwave is interfering with your radio isn't because it's emitting microwaves, because your radio isn't going to be at all sensitive to microwaves. It's tuned to a frequency which is completely different. However, if you're looking at inside the microwave, there's all sorts of other bits of circuitry, quite a lot of them running at mains, and if you've got one of those which isn't working very well, you can have a piece of circuitry which is oscillating backwards and forwards at 50 hertz, and that will produce a 50 hertz hum. You've probably come across 50 hertz hum a lot if you ever go to a gig and you hear this hum over the PA when you haven't quite set it out right. That's because the electricity in the mains is flowing backwards and forwards 50 times a second, and that can emit essentially radio waves at 50 hertz, and that can get picked up by your radio. And so you're probably picking up 50 hertz hum from the mains inside the circuits which aren't properly shielded or not quite made right, rather than things being emitted from the microwaves. If your mobile phone doesn't work very, very well near the microwave, then that is more suspicious, because mobile phones do work on similar frequencies to the microwave, not the same frequencies, but similar ones. And although I'd be surprised if the mobile phone might be interfered by a very, very powerful microwave, by the microwave oven. So I'd be slightly more worried about that than it interfering with your radio.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.